Thank you everyone for joining today, the Julia user group Munich, with a session on the package compiler. You already see a chair from Kristoffer. Kristoffer Carlsson is today with us. I'm very thankful he joined. He is our speaker and he is one of the core developers, maintainers of Package Compiler. He's working for Julia Computing right now and started using Julia already in 2015. That was version 0.3. It's really one of the young joiners, the early Julia enthusiast. He contributed a lot to the Julia language itself. Now, since 3 years, this package compiler is around the corner. He worked on it a lot, and I'm very happy he's today going to share a little introduction with us. So feel welcome to ask all your questions. Yeah, there can be kind of intermediate, beginner, deep questions. I'm have an eye on the chat so that I can raise your voice, but you can also unmute yourself and ask a question directly. So both work. Yeah, so thank you for being here with us, Kristoffer, and then stage is yours.
Yeah, just double checking that my microphone works okay and everything now.
Yes.
Yeah, okay, good. So welcome everyone. I'll talk a bit about the Julia package called Package Compiler. I apologize a little bit if my audio quality is not so good. Usually I'm in my home office where I have a nice microphone and so on, but now I'm a bit traveling, so I had to find the best place I could, but hopefully you will understand anyway. So first, I just thought I would say very shortly some words about myself. As mentioned, I work at Julia Computing as a software engineer. And before that, I was a PhD student at Chalmers University of Technology in Gothenburg, Sweden. And I was doing materials and computational mechanics. And it was there that I sort of found Julia. I was doing finite element modeling, and I wrote some code in Python, and it was slow. And then I was looking for something else. I didn't want to use MATLAB because everyone was using MATLAB, and I kind of wanted to do something different from everyone else. And then somehow I found Julia and did some experiments, and it worked very well for my problems. And then I sort of started just contributing something to the language. I think I started was a lot on the sparse matrix functionality, because in finite element modeling, you typically get very large sparse matrices. So that's sort of how was my main sort of interaction with Julia at that point. And then it kind of grew and grew to more and more wide areas. So yeah, then I started doing so much Julia that I applied to Julia Computing and got a position there. And part of my work at Julia Computing is actually to work a bit on these open source projects and tools. And I also do some work on the Julia releases, actually, to, like, when a new Julia release comes, we're running all the tests for the packages to see that the packages that passed on the last Julia version also passes on the new Julia version. And we have a bunch of performance benchmarks that we also run just to try to see that a new release is not sort of worse than the first one. In many software, it feels like you update your software and the new one you get is just worse. It's slower and it looks differently and so on. So I try with Julia at least that new releases of Julia should be better than the older one and should have so few regressions as possible. There's always some things that sneak in, but yeah, we try our best. And so some of the packages that I sort of help or maintain or work on is the package manager, PKG, a bit on the debugger, the command line interface to the debugger. It's called debugger.jl. And then also, of course, package compiler, which I will talk about now. So to give a little bit of an outline then, first I want to sort of give a brief background about what we call latency and these sysimage, and that's sort of to set the stage for package compiler, like try to explain a bit what's the issue we're trying to solve, why is package compiler useful. Then I want to show how it could look actually using package compiler and some of the sort of timings and how it works. And that is one part where you're creating these things called sysimages that we will go through what those are. And then the second part about Package Compiler is to create what I call apps or applications, but you can also create libraries. And with libraries, I don't mean like normal Julia packages, then I mean libraries that you can call from other languages that expect the C interface. So let's say if you have a big C++ code and you want to sort of offload a part of your program to Julia and run sort of maybe some numerical routine, then you could create sort of a library that would act like a normal sort of shared library that you can open and you can run code inside it. Then I just want to show a little bit about related work, things that are, it's not exactly package compiler, but things that are in the same spirit. It's about compiling things to disk and to cache code and so on. And then, yeah, I don't know, we might have some Q&A in the end, but there's also, I think it was said that we have some Q&A throughout the talk as well. So just ask away if there's anything. Okay, so let's start with the big word latency then. So how do we define latency? Well, in a simple way, you could sort of think about it as the time we spend waiting for work to start happening from when we start Julia. So here I'm excluding sort of one-time costs. Like if you can do some caching before that, that's not part of the latency then, that's part of like the compilation stage. But latency is part of, you know, things you have to wait after you start Julia. So there are sort of two common sources. The first one is the package load time. And that is here I'm loading a package here, plots, which has sort of been a bit notorious when it comes to latency, and that it takes a while to load and it takes a while to run. But first we load it here and I time it, and here it takes about 5 seconds. So that is one part of the latency. But we're not done yet, because then when we're calling a function, we have to compile the function, we might have to do some inference and so on. And inference, for those of you who don't know, is that Julia tries to figure out what the types of everything are, so it can do optimizations, and that can take quite some time. So here we can see I time the time it takes to create a plot object and the time it takes to show it, and it took approximately 5 seconds as well. But now if I plot again, you can see it's pretty much instant. So that this is sort of a part of the latency as well then, that the first time we call something, we need to compile or do some kind of stuff the first time. So the total latency then is sort of when we add up the load time and the compilation time here, and sometimes you call this time to first plot, or it has a nice short name here, TTFP. And if we just add up this number, we can see it takes approximately, on this computer with this Julia version, this plots version, and so on and so on, it takes about 9.5 seconds from when we started Julia until we see our first plot. So depending on what you're doing, 10 seconds can be a very long time. If you're trying to sort of run Julia in some script where you call this over and over again, it's quite a long time. But if you have the same Julia session open for quite a while, then maybe 10 seconds is a short time. So if this is big or not, it depends a little bit on your use case, but of course we always want it to be smaller. So what are some strategies we can do to improve the wait, I went two slides. Okay, here's the first slide. So what is the strategy we can do to speed up the package loading? Well, the first one is something called pre-compilation. And since Julia 1.6, we have this parallel pre-compilation. If you've used the package compiler lately, you probably see that when you add a package, it comes up this list of all the dependencies, and there's these things spinning, and that is sort of the parallel pre-compilation. Here, I'm not doing the parallel one, I'm just loading it here with using plots, and then it doesn't do the parallel one, which is usually very slow. In the future, we should probably make it so that if you're trying to load it like this, it does the parallel thing as well, but for now, the package manager typically handles it well. But here, I cleared out all my like cached compiled files and just did a using plots from scratch, and it took about 100 seconds then. If we want, we can turn off using package pre-compilation by adding a Julia flag. If you do this --compile modules equals no, then it's not going to use any of this pre-compilation stuff. So we can just see how long time does it take to load plots then when we're not using the pre-compilation. And here it takes 35 seconds. So 35 seconds is shorter than these 100 seconds for sure. But the point is that if we do this pre-compilation step, then we can we pay a one-time cost, and then in the future we have faster package loads every time we want to load plots. So here we can load plots, as we saw previous slide as well, it takes about 5 seconds. So instead of it taking 35 seconds every time, we do like a one-time caching thing, and then it's faster after that. And this cache file that is being created when we load plots, it's tied to the specific version of the package. It's also tied to the specific version of Julia and the version of the dependencies and so on. So if you do a big package update, for example, then you're going to have to pre-compile your stuff then. But while you're sort of using the same versions of everything, this cache file that's created here is valid.
Kristoffer, one question from me.
Yeah.
This first part and the second part, the difference is just that the first does not run things in parallel, or is there also another difference? I mean,
this part and this part. Yeah. This first part here is that it's one thing is that it's not running things in parallel, so it has to do all the pre-compilation in serial, and then it loads the package. The second part here is that it doesn't do any pre-compiling at all. It doesn't try to do this caching step. It just loads plots straight away without creating this pre-compiled cache file. So you can see that there is a cost to create this pre-compiled cache file because this is faster than this one. But the point is, if you create the cache file, then you have significantly faster load time every time after that. So it's sort of an investment. You pay in a bit of time in the beginning, and then you can get the dividend here where you have smaller load times in the future.
Thanks, got it now.
Yeah.
May I ask also a question?
Yeah.
So what exactly is loading? So you mentioned that it does loading without precompilation. So what exactly do you mean with loading? What happens in this time?
Loading means that, for example, plots have a lot of dependencies, and in each dependencies there are methods. So what loading is basically take all the methods from all the dependencies and sort of incorporate it into the Julia session. And there's not only methods, there's also structs and so on. So you sort of need to take everything that's been, well, if you don't do pre-compilation, you basically have the source files. So you have to go through the whole steps. You have to parse the source files, you have to do something called lowering. Then after that, you have to sort of define all the methods get defined, and they have to get inserted into something called a method table. You basically need to get you to the point that you can start calling methods. If you don't have anything cached, then that can take quite a while to do this whole thing. But when you cache things, you don't start from scratch, basically. You start from a further point. If you think about a compiler, it's sort of a pipeline from source files up until the end where you have sort of machine code. And the more to the right, from my point of view, I don't know if my camera mirrors me, but the more to this direction you can sort of cache, the shorter distance you have until the end result, sort of. So what you have here is that you kind of start from the left and you sort of go through the whole thing without caching anything. With this thing, you kind of do a bunch of stuff here and create a file that's sort of somehow in the middle. And then when you load it, you start from the middle instead, so you don't have to go the whole way. And we'll see here with Package Compiler, the point is sort of to push the caching strategy even further to the right, so we're closer to our end goal when we load the file. So that's package load.
There's one further question in the chat, which perfectly fits here. And it's asking, so now assuming we are in this third step, and the using plots takes 5 seconds, what is Julia actually working on in these 5 seconds?
So the most thing it does is that there's a very many methods here in plots and in its dependencies. It has to take all these methods and insert it into something called a method table, and it has to sort them based on sort of Julia uses multiple dispatch, so it has to sort of sort them based on different what types of signatures there are and so on, so that when you call a method with some signature and some types, it has to be able to look up which one's actually gonna run. There's also other things that can happen in that. There's something called invalidations, and what happens then is that it's possible that earlier code you compiled, optimizations you did there are no longer valid after you load some new code. It's a little bit advanced, I'm not going to go into the details there, but what can happen is that when you load a package, it has to go and recompute some stuff it did earlier, because some assumptions it did back then might not longer be true when you're loading sort of new data. You have a new world, a new view of the world, and your old view might no longer be the true, and then you have to sort of recheck things. So
thanks. Yeah. So for this example, it's really just integrating the cached pre-compilation into the currently running Julia.
Yes, and that is a good description of it. Yes. So that was sort of the first part, and then we can look at some strategies for improving the sort of first call latency, or when we're actually calling functions. So one thing we can do is to reduce the optimization level. So this is globally then, so you can say give a -01 to Julia, and all of a sudden, instead of 4.7 seconds, which is with the default, it takes 2.7 seconds. And that is because with 01, a bunch of the optimizations that Julia does, and Julia also uses a library called LLVM, which does a lot of advanced optimizations and so on, which can be a bit slow. And for a plotting tool, those type of optimizations is unlikely to be very beneficial in the end. I mean, it takes some time to run them, but in the end, the code might not be a lot faster. And unless you plot very, very big data sets, then maybe you're not really going to notice a difference. So that is one way to do it is you just take down on your optimization level, but it's a little bit, you probably don't want to, like, let's say you're running your number crunching code in the same session as you're running your plotting code. Then you want your number crunching code to be running with full optimizations, but maybe the plotting only run in 01 optimizations. And you can set this optimization level at what I say module level granularity. You can set it on a specific module. So I think this is a link. So this is a package called argparse, which what it does is that it parses arguments, and you want that to be really fast, right? Because it happens just when you start Julia. So what it does then is that there's it's a bit complicated syntax, but basically what it can say is that it sets compiler options and it optimizes equal to 0. It doesn't infer code. It compiles as little as it can. So what it's doing is very heavily optimizes against having a low latency. And then the code might be a little bit slower, but that doesn't really matter because all it's doing is parsing 5 command line options. And if that takes 10 times slower, it's still not going to be a bottleneck in your code. So this is one way packages do to sort of say that, okay, it's fine, don't optimize me so much because I don't really need that. So not all, as I say, not all codes benefit from running with this O2 then. So if there's a possibility of using lower optimization, gives faster compile times.
One question from the chat.
Yeah.
I think it's again referring back to the using plots taking 5 seconds or more. The question is, why don't other interactive languages do not need to do this 5-second things? It does not take 10 seconds to plot in MATLAB, for instance. Like, is this a Julia drawback?
I would think that if you time the time it takes from starting MATLAB to plotting something you get up on your screen, I don't think it would be much faster than 10 seconds. I don't have MATLAB installed here, but I do know that MATLAB do some JIT compilations, and I think one reason people feel MATLAB is a bit faster when it comes to this is that they typically have MATLAB open much longer than, you very rarely have to restart MATLAB, but for various reason you restart Julia. It would be interesting to see a timing from like 0 MATLAB, like double clicking it on the desktop, and then how long it takes to get a plot. It's probably faster than 10 seconds, but I remember checking something like that, and it's also faster the second time you do it over the first. And another thing with Julia right now is that it, like with MATLAB, it doesn't really have a package system where you have files sort of that you include, but you don't really have a package system like this. And if we take Python, for example, where you can import a library that's like a big library, let's say NumPy, and without it taking much time at all. With Python, it doesn't do much things at all with the library because it runs the things interpreted. So it does create the cache file, but that one does way less than Julia does. It doesn't do, for example, type inference, and it doesn't do many of the optimization steps and so on. So it needs to do much less work. And then I think, of course, as I will show actually later, there are things that can be done to bring this down as well.
I think here's a misunderstanding. It's not about, we are still not plotting. It's just importing, right?
Mm-hmm.
So I think the question was about plotting. We haven't line plot or bar plot. We just imported, and this is time needed for the import.
Yeah, I think what I said before is a bunch of these method insertion that Julia have sort of a multiple dispatch, and you have sort of a global method table where all the methods are in there, and they have to be sorted and inserted and so on. And there are things that are cached in here like inference results and so on, and all of that has to go into their correct data structures. Like what's saved is sort of in a serialized state, but when you load it, it has to be sort of put into a new data structures.
Thank you.
So, but I don't have the exact profile on all the different steps that end up taking 5 seconds. That would be interesting to have a good overview. It's possible to do a profile on this using plots, and you can sort of see a bit on the profile output, but unless you know a lot about Julia internals, which I don't really do myself, I would say, then it's a little bit hard to interpret the output. Okay, so then we talked about the actual calling plot, and then another possibility for sort of improving this first call latency is to prevent something called specialization. So with Julia, you're compiling a new function for each sort of signature or each type of arguments you provide. So if you have a function f here, and you call it with the float 64, it's going to compile one version. If you compile it with an integer, it's going to compile another version, and so on. What you can do is to put no specialize of x on it, and then it's going to compile a generic version of it that works for all input types. Now, this will necessarily mean that this function will be slower, because you cannot do the same assumption. You cannot do a strong assumption as you could if you knew the exact type. I would say this is not so frequently used in like normal user code. Like the compiler itself uses quite a lot of these because it needs to handle like a bunch of different types that are going to run the same code, but it doesn't want to specialize in all of those types. But I just put it here in case you see it somewhere, then you know what's going on. So if we sort of summarize the latency reduction strategies we have, is that we can cache part of the compilation. And this presentation is sort of a little bit about how we can cache more than the standard Julia precompile system. So we can cache more, we can compile less code. So what I'm doing here is that we're compiling one version instead of many versions. or we can optimize less. That means that it's cheaper per function or per method to compile it. So those are sort of the three strategies we have to bring these numbers down. So if we do a little bit of evaluation of these latency reduction strategies that I've showed so far, we have package precompilation, where the loading time can still be quite significant, unfortunately, but it's kind of automatic. It happens by itself. The package compiler does it in parallel, sort of, so that's a good thing. We can do a lower optimization level or do these no specialize, but this can impact the runtime. Let's say if your function was you really needed the extra optimization level, and even with these, the latency can be pretty high. And a lot of functions don't really benefit from having this super high optimization level. So that sort of means that it's okay to do it from time to time. And improving latency is like a high priority. I think there's a link here to the issue tracker that has the latency label on it. And you can see here there's a lot of open things, but there's also a lot of closed issues, and sort of all of these that have to do with latency is about making these numbers that I've shown so far smaller. But even though this is a high priority, it will never likely be sort of super instantaneous to start Julia and make a plot with the strategies shown above. It's just like the way Julia works, there has to be some sort of work. So this is probably going to take a little bit of time, but of course, as I will show later, there's some pretty cool work that's ongoing right now. But we can try maybe a different way than just the standard stuff. So if we think a little bit about the standard libraries then, so Julia comes with a set of standard libraries. You can click here, it's going to take me to where the standard libraries are here, and there's a bunch of them here. And if we try to look at, okay, we can go back and we can look at them. Let's say we look at the REPL. It kind of looks like a normal package here. It has a source directory test and a TOML file and the source directory here, and here's the REPL file, and oops, it has a lot of code in it. And same with the package manager, for example, it's structured like a normal packages, but if we look how fast PKG loads, it loads pretty much instantly here. Like here's a 1000, this is 1,000 times faster than what it took to load plots, for example. So how is that possible? And can't we do the same for our packages? Like, is the package manager kind of cheating here? Why can it be so fast while the other one, while we have to wait 5 seconds to load plots? We want to do the same for PKG here as PKG do. And then comes the concept of a sys image. And you can kind of think as a sys image as a Julia session that's been serialized to a file. So here I looked at, I have a Mac here, and I looked at, there's a file here in this this directory here. It's a 1.8 version install. And if we look at it, there's a file here called sys.dylib, like a dynamic library, and it's pretty big. It's 186 megabytes. And in here, you can kind of think that there's a whole Julia session in there, and that includes standard libraries, and it also includes compiled code, but also documentation and everything sort of that you can do inside Julia, or not everything, but a lot of the stuff are in here. And these are loaded into Julia when the sys image is created. So Julia has a step when Julia is created. And then here are a bunch of the standard libraries, and these gets loaded into Julia when Julia is compiled. And then they get put into this sys image format as stored in here. And we can see that even though this sys image has so many standard libraries and stuff in it, it's pretty fast to just, when we start Julia, we're loading the sys image. So all these packages, in this case, it was 0.3 seconds on my machine here, which is not super fast. But if you think about how many packages are loaded just by the sysimage, compared to how long a time it took to just load plots, you can see it's a significantly more efficient format to store things here. So I have created a sysimage here that has no standard libraries in it. So I'll show a short little demo here, but I can also just see what happens here. So if I don't have any standard libraries in my sysimage, then when I load package compiler, it has to precompile it just like it was a normal package because it's not in the sysimage. And then the second time when I load package compiler, it takes, doesn't take as long as plots, but it takes a while to load it here because now it's acting like it's a normal package. And if we look at this custom sysimage that created, it's much smaller than the standard one because it doesn't have as much in it anymore. So let's see if I can do this. If I go back to my terminal here, and let's see if I have it in my history. So now there's a flag here you can give to Julia where you can give it a custom sysimage, and I have created one specially here that has no standard libraries in it. So firstly, it's saying that a REPL provider is not available using basic fallback, and that's because the REPL is not in the sysimage anymore. So there's no REPL. What happens then is that Julia has like a very small REPL that does not have at all as many features as the normal one. I think this one is in C, so you can't do like the normal movements and so on. But if I'm trying to load the package manager here, you see it took a while here to just load it compared to how it usually is when it loads instantly. So this is sort of how it would be if PKG was a completely normal package. Then it would take this amount of time to load it. Here, and yeah. So we can see that loading standard library is fast, and then how about the first call latency then? Like how long time does it take to call the thing for the first time? But if we have the default sysimage, I just did a time here to PKG status, it took 0.5 seconds. And if I took a custom sysimage that didn't have any standard libraries in it, it took almost 10 seconds here. So not only does the sysimage help with time to load the package, it also helps the time to call things for the first time. So how does it do that? And can't we use that for our packages? Well, the way Julia works is that you typically have a generic method. Here I have a do something of X. And here the type of X is not specified. So depending on what we call X with, we're going to compile a new version of it. But how do we know what types to compile a method for? Like it's not until we actually call it that we know. If I just gave you this do something X and I would say generate efficient machine code for this, you would ask me, well, what does the type of X have? Like if it's a float 64, I know how to do it. If it's an integer, I know how to do it. But if you just give me X, I don't know. And it's hard for Julia to predict what is actually going to get called here, because that's sort of a runtime thing. But an idea could be that we sort of have a representative workload. Let's say for a package manager, it might be to add a package. That's a sort of a representative workload. And then we record what types of every arguments to functions are. And this is a little bit similar. There's a thing called profile guided optimization. And what you do then is you compile your program, then you run a representative workload, and then you compile your program again with data based on that workload, and you can do some more optimizations because you know things like, oh, this branch is almost never taken, so we can put that last, or this function, maybe we should inline it. It's a little bit like that, except we are using this representative workload to actually know what we should compile. So if I click the link here, you can see this is a part of what Julia does when we're creating Julia itself. So there's a thing here called precompiled script, and when it does it, that it enters a few things in like a repo, and then it records exactly what the functions end up getting compiled and what types or the arguments are. So there's also here for PKG, there's a little script here. What it does is basically it creates like a fake registry and it adds some test package and so on. And while it does that, it sort of remembers what types the arguments had to it, what types the arguments had to the PKG functions. So one way we can do this is to see what things actually get compiled. And so here I have a file, I call it example compile.jl. It has some function f in it. It does very simple math. And then we do call this with 3 different type of arguments, with a 1 and a 1.0 and a matrix here. And if I give this -- trace compile flag, I can choose to get an output of what things are actually getting compiled. So I can do a little demo of that. See if I have that in my history. What was the file called? It was called example compile. So I can just cat this file. So this was exactly what I had on the slide. And when I pass this -- trace compile, and stdr is like a special name, it's going to just print it out. But if you want, you can also give it the file. So if I give it the file, instead of saying stdr, maybe I call it precompile file.jl. And then if I cat this precompile file.jl, you can see they are in here. So this is sort of a way to record the execution of a Julia script and see what things actually end up getting called and compiled. So here we see we call the function f with an integer, a float, and then an array, matrix here of integers. So we can sort of see how much do we have to compile when we start Julia. So if I just do a trace compile is equal to standard error, and I just start Julia, you can see there was 2 things that needed to be compiled. For some reason, these are not cached. It might have to do with that when this recorded script is getting run, there's some difference between what I'm running now. If I do something, it had to compile one other thing. But in general, it's very little here that has to be compiled from starting Julia when I'm using the normal sysimage. But I also have another custom sysimage here that does not include any sort of pre-compilation. It doesn't include any cached code. So it still has the sysimages in the it still has the standard libraries in the sysimage, but it doesn't have, it didn't run those script that I showed before. That was in this link, remember, the one that did all this example workload so we could record what it was. So I have this call, it's called stdlibs no precompile. So it's stdlibs no precompile. So I load this sysimage, and now I also tell it to print out everything it compiles. And you can see here now that it prints out way more. So this is sort of all the things that it had to compile now when it didn't cache anything. And if I just start printing a little bit here, if I press enter 1 + 1, you can see how much it compiles. But if I write 1 + 1 again a couple of times, it doesn't have to compile it again, of course. So now we're in here, but let's just say like throwing an error like that. There's a lot of things it has to do. So you can see that we save a lot of, or if we cache pre-compilation, or if you cache compiled stuff, we don't have to compile it again when we start Julia. So if we look a little bit like a conclusion or an idea for a tool then to help with these latency stuff is that we know deserializing a sysimage is fast, and we know that we can put in standard libraries into the sysimage, but what if we can put in a list of our own packages in a custom sysimage, which is in a very similar way to how standard libraries are put into the sysimage. Putting them into the sysimage would make them load very quickly. And then the second step is we can also give a representative workload similar to how the standard libraries do it. figure out what types to sort of compile these specialization of generic methods onto. And then we just start Julia with that custom sys_image. And then this whole process above, if we bundle this in a nice API, then we might have sort of a useful tool. And one part of Package Compiler is pretty much exactly this slide. It does the above stuff, but in a sort of a nice API.
One question from the chat.
Yeah.
Quite specific already, but maybe you can answer. Does Snoop compile do the same or more than this way?
Snoop compile does very similar to this trace compile stuff, but it can do it in an already running session. You don't have to start it with the -- trace compile. You can basically start Julia, and then Snoop compile can sort of activate and deactivate the printing of this stuff. And you can also use Snoop compile. You can sort of filter things, and it's a little bit more user-friendly, I would say, than this flag. This flag was a little bit easier just to show things because you don't have to load a package and so on. You can directly do it from the command line. But Snoop compile does, there's a pretty big overlap with what this stuff is. And for those of you who don't know, Snoop compile is a normal Julia package, which also just trying to help around with different things to improve the latency. So that was sort of the background, and hopefully sort of the problem or the task that we want to fix, or at least improve, is clear. And so then how do we do this? If I go back one slide, this strategy that I presented here, how do we use Package Compiler for that? So let's just see how we use it. So we just use the package compiler like a normal package here. I'm just loading it. And then we use it as a function here called create sysimage. And then we give the set of packages we want to give as a list of symbols. Strings are also possible, I think. And then we give the output path of the sysimage where we want it to be saved. And then package compiler says, okay, I'm creating a sysimage here. And it takes a little while. But now we have this custom sysimage after it. And we can start Julia and loading this specific sysimage. I call it sysimage plots here. And then we can see that loading plots is very fast. And there's actually doing the first call is also much faster here, and that is because if you go into plots, they have a bunch of these. If I go back a couple of slides, these precompiled stuff, they already have that in the plots package. So they already say like, okay, generate code for these type of functions. So with the sysimage, it also got a bunch faster to plot things for the first time. So we can demo this. It was called sysimage plots. Let's see if I have that in my there. So now I'm loading Julia with this custom sysimage. Let's just go up here, and now we can see, and you can see that it loads very fast now because it's inside the sysimage. So in some sense, it's already loaded once we started Julia, and we can look at the time it takes to plot something, and it was about 0.6 here. So that's significantly faster than what it was before. If you remember, I think it was 5 seconds or something when we didn't have anything. So yeah, we just said what was the package, where should the output be, and we have this sysimage, and we just tell Julia to use that one, and then we have fast loading. So one thing we didn't say, we didn't provide sort of a representative workload here. We just said here's plots. But we can also say is that, oh, this is the type of scripts or types of codes we're going to run. And could you please record, like I showed before with the trace compile command line flag, could you please record all the stuff that needs to be compiled for this thing to load? And then could you also cache that in the sysimage? So what we do now is the same thing as before, but we also give it a precompile execution file. So that's this file here. And if now it takes a bit longer to create the sysimage because we're also executing this and we're generating code for this and so on. But if we now call the sysimage here that has a underscore precompile in it, let's go back here. What's it called? Sysimage plot precompile. Sysimage plots precompile there. Why this one? Then we can load plots and we can plot here, and as you can see, I just think that it was 0.38, so that's still quite a bit of time. But there's actually a constant overhead here. If I close the window and I run it again, you see it takes 0.3 seconds. If I close the window and I run it again, it takes 0.3 seconds. But if I just don't close the window, it's fast. So I think this is with the GR backend that plots use it. It's like for it to create a new window, it takes about 0.31 seconds. And that has nothing to do with the compile time. It just, I don't know exactly what it does, but something takes some time. So it's not really fair to look at this 0.38. We should kind of take away 0.31 from this. So it's actually like 0.07 here. And if you go back a slide, this would be 0.3 approximately. So we went from 0.3 to 0.07 here. I wrote it here in sort of like a comment here that 0.31 seconds is the opening of the window itself. So the idea here was that we provided a file with the representative workload, so we could sort of record everything that gets compiled, and then we save that in the sysimage. So if you want to evaluate then a custom sysimage, we have pretty fast package load time. We have a low first call latency with the training script. But there's some drawbacks here that we lock to a set of version of the packages that gets put into the sysimage. So you can't really do a PKG update and get updated packages when you have a sysimage. That's also true for all the dependencies. So when we're using the plot sysimage, we're kind of locked to that plots version. And if we update our package, we have to create a new sysimage. And it's a bit slower to generate these than the normal package precompilation. And it's not automatic. You have to kind of explicitly load the sysimage. This or replace default should not be here anymore because you can't do that anymore because that's a bad idea. But this is a good idea to use if the load time and the first call latency is long enough to be annoying. And if you're not frequently changing the package versions or changing packages you have, then you can use the same sysimage for a while. For example, some stuff that might be good to have in the sysimage, for example, revise, because that's sort of a thing where you want to load some. I want to load revise almost all the time because I like the features that provide. The debugger could be in there, or if you do a lot of plots, you can put plots in there and so on. So that's sort of an evaluation of sysimages then. Then the next step is, I'm just going to check the time here. It's got a little bit now, longer time than I thought, but let's go through this as well. So we can go through here creating apps or libraries with PackageCompiler. So an app, what is an app then? Well, it's sort of something that you're not using as a library. Like you can see that, let's say, what should we take? A notepad in Windows, that's an app. It's not something you're using from another application. It's just like the thing you're actually using. And one way you could do this with Julia is that you install Julia, you use the Git in the package manager to download a package, then you have some manifest file, and then you can load the package and sort of start the application. So we have a little...
Kristoffer, one little question to the previous part. Is it possible to exclude modules such as GR to make the sysimage smaller?
I think it's not really possible because if you exclude a module, then you have to exclude everything that the module everything that depends on that module as well, as it is right now. So we could add such a functionality that you could exclude some stuff, but then everything above it would have to be excluded as well, because it's trying to load that. So it has to sort of be self-contained, the whole thing. So yeah.
Thank you.
So just want to go into this Redux app, and then I'm gonna run a function here, and this is a little application. It's like a to-do model view controller. It has a little list here, like what needs to be done. I'm sorry if the text is small. I'm just going to write some things I need to do. So have presentation, and then answer Q&A, and then when I'm done with them, I can click here, and I can clear what I have completed, and that's a little toy application here with the graphical interface and so on. And yeah, but it would be nice if we could, instead of having this as a Julia package where someone has to install Julia, they have to download the package and so on, if we could just send like the application to someone else without requiring them to have a Julia installed. So we can think a little bit how Julia itself is shipped. So we have Julia has the runtime libraries. It has some other libraries like LLVM, OpenBLAS, libgit2 it uses. It has a sysimage with packages or standard libraries and compiled code in it. And then it has an executable that initializes Julia and sort of starts the repo. That is kind of Julia itself. Now, we could sort of copy that almost, but with some differences, then that we use a custom sysimage that have our own packages and our own compiled code for good latency. And then we bundle the Julia runtime libraries. We're going to need those as well. And then instead of the executable that starts up the Julia repo, we have our own executable that starts up our app. So, and then there's no need to bundle the source code or anything. Everything is sort of contained inside the sysimage. So for package compiler, there's a create app function. So what it takes is that it takes the name of where the app lives, which is a normal Julia package that has a special function called Julia main, which is what's going to get run. Then the output, where the compiled version should be end up. And then the same way we can give it some kind of a script here that runs it. And this took a long time because I think in this in this script it popped up a window and I forgot to click it down for a long time. So it was just waiting for me there. So it took a long time. But anyway, it creates a sysimage with this Redux app package in it and all the dependencies. It bundles the Julia libraries. It bundles these things called artifacts, which are external libraries used by packages. So for example, in the little app I just showed, it showed a window, right? So the library that showed that window was this library called cgui. And then it creates an executable that runs the Julia main defined in the package. So go back here. I have the compiled version here. We can go in and look how it looks here. So we have a bin directory, which it has a normal Julia executable, but it also has the special executable in it. If we go to lib and Julia, it has a bunch of stuff bundled here that Julia might need. And now if you want to run this, we can just do bin and then do the app. And then here we have the exact same thing. But the point now is that you can take this folder and send it to someone else, and they can just run it, assuming it has to be the same sort of architecture or same operating system. So here I'm on a Mac, I can send it on a Mac. Or if I create it on Windows, I can send it to another Windows machine. It's a similar way that you have different installs for Julia depending on your operating system.
One question.
So
to scan. And can everything be packed into an app, or are there limitations? I remember a while ago a situation where I tried to create an app which didn't work because some package had an external dependency, some DLLs, I think, which could not be handled.
Yeah, I'm gonna go through that soon. Actually, about this is almost exactly about this. So, I mean, the first point here is, so can we make apps from all Julia packages? So I think the question might be answered by just going through the slides here. Kind of yes, but there's all dependencies need to be what I call relocatable, and that is that it can't really embed too many assumptions about the machine that the app will later run on at the point when you create the application. So I'll show some example if that's a bit confusing. So some packages, what they do, there's not so many anymore, but what they used to do is that they had sort of a thing called the build stage. And what that did is that, let's say the package needed a certain library. When the package was built, it found this library somewhere on the machine, like it's in dash user dash lib dash da da da, and it found that library. Then it wrote a little file here where it set a const variable name to that path. And then inside the package, it included this file it wrote, and then in the init file, it sort of DL opened the path or something. So the problem now is that this find library function, it found an absolute path. Maybe it has a username in it, like home dash Kristoffer Carlsson dash something. Now, if I send this to someone else, this path will not be updated because this is a part of the compilation. It happens on the machine where you create the application. So then this path will not be available. So if you try it, run it, then it's going to be like, oh, I couldn't find dash slash home slash Kristoffer Carlsson because it's on a different machine with maybe a different username or something, or the thing is installed somewhere else. So what's good now is that we have a thing called the artifact system. And there you can, if you just use that, this problem won't happen because things are encoded in like, it doesn't rely on absolute paths anymore. So it can find things. So if I go back to the compiled app here, and then inside the share folder, Julia, then there's the artifacts, and here are all the artifacts that this application needed. They have funny looking names, but they are, here's libgpg, apparently was needed, and Julia knows how to find these.
Definitely two questions in the chat meanwhile. First one, the apps usually open a console window. Since the example you showed was a GUI app, would it be possible to not open the console, such in Python is done with Python W?
I'm not sure actually what happens if you, like, let's say you make a shortcut to this one here. If you make a shortcut to it, or like you double click it, if it's gonna pop up console window or how it is. Maybe I don't actually know. It would be good if that could be sort of suppressed somehow to not show up a console window if you don't want that.
Second question, is there any chance we can get cross compilation so that create app would create the app for many platforms?
Yeah, the problem here is that Julia itself doesn't really cross-compile. You can create something called a libjulia in a cross-compile way, but to sort of create the whole Julia bundle, you kind of have to run Julia code. And there's no cross-compiler for that, since you actually need to run Julia code itself, sort of. So the way that would be done would be somehow have some sort of emulation layer where you run it maybe using some virtual machine or something, and you create it in there. But like actual true cross compilation, I think it's not going to be there for quite a while. So another, was there one more or?
No, that was it.
Okay. So another issue is if you're including source files at runtime, because when you're running the app, you don't have any source files, you just have the sysimage. So if you somehow try to think that, oh, I'm going to find this file during runtime, then there might be problems having it as an app. But as more and more packages move over to the artifact system, it becomes better and better. And like before, when we started with these things, like no one thought about this stuff, so it was very bad. But now there's sort of best practices that are establishing, so this becomes less of an issue. So let's do a little evaluation then of Julia apps. It's possible to distribute apps made from Julia packages that just runs. They have decently low latency thanks to sysimage and precompiled script. But here, an answer to the question here is it doesn't have cross-compilation, and there's pretty big size overhead for small apps. Like if you just write like an LS or something like that, then the size of the whole bundle will be too big for it to make sense. But if you have like actual sizable apps, then maybe size overhead is not so bad. And having to automate this precompiled script can be a little bit hard if you have like interactive packages. Like, let's say that in order to have a representative workload, you have to plot something, you have to click around and so on. You typically don't want to have to do that every time you make the app, so you have to automate it, but that can be a little bit tricky. Julia libraries, I'm just going to go very quickly, but that's sort of, instead of creating an application with as a binary, you create a shared library that you can call, for example, C. I'm just going to leave the links here, and for those that are interested, they can read it. This libcg is an example. There's a CG here, is a conjugate gradient. It's an iterative linear solver, and in this repository, you can see how you use PackageCompiler to create the library from that, and then it also shows how it's getting called from C. I think there's an example of it getting called from Rust and maybe Go. I have to click on it to see. No, C and Rust is in here. So we can just very quickly see how it looks. We can look at, this is sort of the Julia package that we want to create the library from. And it's very simple. It has it provides this C interface, which is this B-based C callable that takes some pointers, and then it creates Julia arrays from it, and it calls the Julia function. And then on the C side, you use PackageCompiler to create the shared library with this that you link to. And then on the C side, you have to initialize Julia, sort of initialize the runtime, but then you just call the Julia's CG here, which it was called, it's just as a normal C function, and you get the C result back. So this is sort of in here, it's a Julia code running, and the Julia code provides a C API for it to get called. Just really quickly then, I just want to show some of the related work that also is going on here. So PackageCompiler.jl, which is a way to sort of actually compile Julia code similar to how you would compile C code. But here you don't really get any runtime support, so this only supports this kind of a small subset of the language. But the goal is to sort of expand on that subset and make it, more and more useful. So the way you would do it here is you would load static compiler and you define some method. Then you can compile this method to a file. And if we look at the file here that was created, here's the O file, the object file. It's very small. It's like if you would have compiled this with C or something. And then you can load this function and call it. But this object file you could also just link with you could create a C library using this object file. It's just a normal bundle of compiled code at that point. So what this load function does is basically it figures out, I think there's some metadata in this file, and then figures out like, okay, this is the types that it supports and so on, because that's not a part of the object file. This is kind of like a header, maybe I would say. So that's pretty exciting stuff, to be able to like actually compile Julia, more and more of it to the actual things, for things where you want to sort of use Julia as a, maybe you want to run things on a microcontroller or something where you cannot have a runtime. You need to have a very small file, small executable. Oh yeah, and then there's also this. Right now, when you're using the standard precompile system, it doesn't cache any native code. It doesn't cache any sort of the assembler code, or the code that the CPU actually runs. The only way to do this with the sysimages. But there's some upcoming work now. It's unclear if it's going to be in 1.9, otherwise 1.10, which will allow caching native code using the same system as the precompilation system. And I've seen some numbers from that, and it looks to be, in some cases, give a pretty good improvement. And the good thing about that is that you don't need to manually create sysimages and so on. It's going to use the same system as the precompilation system, where things happen automatically, sort of. And while this gives a significant improvement, I think sysimage will still be sort of the king, or the actual best way if all you want is to have this low latency, because with sysimage you have sort of everything in one package and you load everything at once, while with normal packages you can load things in different orders and so on, so it's hard to do the same optimizations that you can do with the sysimage.
There've been a couple of questions already, but yeah, decide please yourself whether you want to finish first and then.
Yeah, I think it makes sense to just finish and then we can go through the questions. So I just put some useful links here, and then I have a link to the slides here on the first slide. I'll go there soon. But the docs for the package compiler, the artifact system, the stuff on the embedding is interesting. It's a little bit more advanced, but if you want to call Julia from C, it's useful. Tim Holy has some blog post about, I think I mentioned a little bit about invalidations and Snoop compile and so on. And then there was a JuliaCon talk on the shared library stuff that I briefly mentioned. And yeah, if I go back to the very first slide, just to have the link up while I answer the question here. Actually, let me see if I can do this. Oh, where did it go? I'm just going to copy it to the. Oh, did I call? No, wait, it's here.
We can still see you, so it has to be somewhere.
Yes. There it is. See if I can click it into the chat. Oh, wow, that turned into very big text. Okay, whatever. You can click the link. That's interesting, a chat box that supports the. Okay, I don't know why it did that, but yeah. So I think that was all. We can go through the questions that you have.
I think you see the link is going to your Google Slides. Yeah, thanks.
Yeah.
One question which already got an answer from another participant. Thank you for that, but still repeating it. Can you say a bit more about the compatibility of the binary in terms of what are the constraints that it can run on different machines? Like, I can imagine constraints like having the same glibc on Linux, or compiling on Windows 11 maybe cannot run on Windows 7, matching macOS versions, etc. Thank you.
I would say it's, if we go to Julia download, we can see here that when we want to download Julia, there's a few different choices we have here. So I would say it's sort of about the same thing here. So it's the libc for Linux. If you're doing on the Mac, if you have an ARM or an Intel. I mean, if you have the ARM, you can emulate Intel stuff, but you can't send the ARM one to an Intel machine. If you have FreeBSD, then yeah, that one is special. So the way the package compiler apps are done is very similar to how Julia itself is done. So it's sort of the same sort of compatibility story as Julia itself has.
Yeah, thank you. I think this answers it. And the further question is, in terms of speed, if I want to run a Julia function from command line, is it faster to use the C library or the sysimage, or both have similar overhead?
There's similar overhead because when you start, it might be slightly faster with the C library, but only slightly, because it's going to end up doing kind of the same things as Julia itself does. Because the main part is, if I have this still open, here, this is the what we call C. It does this init Julia, and that's sort of the function you have to call in the start to call into Julia. It sets up everything that Julia expects it to be, and this is has to be called if you're doing the C, but if you call with the sysimage, this is also going to be called. So I would measure it, but there probably won't be that much of a difference, I would say.
Thank you. Further one. Big thank you from one of the participants. And the second questions about app creation. Is there a list of all the packages that are ready to be pre-compiled, made into an app?
There's not a list, and the thing with an app is that you kind of need to have a main entry point, so the thing that starts up the thing. And if you think like a normal Julia package, it doesn't really have that. Like, let's say, what should we take? Like a nearest neighbor package. It doesn't have like a start me function that sort of presents something. So you kind of need to write an app with that in your sort of head, similar to how the Redux stuff. Here it had this.
Kristoffer?
Yes?
Can I specify questions more about, let's say I have a huge package that uses a lot of different apps. And from my package, I like to do an app, like create an app. And I had the issue that quite some packages, this was like half a year ago or a year ago, were like not working. And then I thought, okay, it would be great to have such a list to see which are already like ready to use.
Yeah, I think the issue is that there's so many Julia packages, and having a list will very quickly get sort of out of date maybe. I would say that most of them should work because most of them are kind of normal, but then there are some of them that do like very special stuff, and those can be a bit problematic. But yeah, if someone wants to sort of take a list, but also the issue is that someone has to go and sit down and like try a bunch of packages and try it. So it's a little bit hard to have a good updated list, I think. I know that we have this thing called PackageCompiler that we use to run the test for all the packages. I know there's a version of it that sort of creates a sysimage and then tries to run the test to see if the test work with the package in the sysimage instead of the package being normal. So that would sort of give a little bit of a list, but there's some other issues with that, is that oftentimes packages do a little bit of strange stuff only when they're testing. So even though their test fail, they might work fine in normal usage. So it's a little bit hard to get a good list like that.
Okay, thanks a lot.
Next question on the list is, can I save the current running Julia session to a sysimage?
Not really. It would be, I think maybe I have an issue open about that, or there was an issue on PackageCompiler. Like, let's say you start Julia, you like load some packages and you do some work, and then you just want to say, okay, save my session, and then you can load it up again. one issue is that there's a bunch of things that are currently sort of going on here. What should be possible is that you should be able to save your session and then have Julia exit. So you would say something like save session, and then it would save the stuff and Julia would exit. And I think there is some pull request. I don't know. I don't want to dig around too much, like looking for stuff while I'm presenting, but I think there was. I'm not sure now, but there was some stuff to try to make that work, but it didn't really work. It doesn't mean that it can't be made to work. It's just that no one has gotten it to work yet and put in the understanding in time. So I think it should be possible.
That would be definitely the most intuitive way for users to create a sys-image.
Yeah.
There's another question. Is there an automatic way to update a sys-image?
Not really. You would have to, like, let's say you have a sys-image that you created from a project file. You would basically have to do, like, you update the packages and then you create a sys-image again. So you could sort of create a little script, I guess, that calls the update function. Oh, look, there's a new plot release since I made this yesterday. So that would sort of be the way to automatically do it. I guess you would load the package manager and tell it to update, and then you would recreate the sys-image. That would just be a few lines, so wouldn't really be that hard, I think.
Yeah, thank you. That was a bit more complex, the question, but yeah. So you need to recreate it. There's no way to kind of change only parts of a system image.
No, that's, I mean, then that's a little bit a thing why it can be fast. It's because it's sort of one thing that you just load straight away. Like there's not many options and there's not many sort of branches. Like with the normal packages, you can load them in different orders and you can load a few of them and so on. And that having all that flexibility also costs a bit of in time, but with the system it's just like all or nothing, blam, there you go, which is why it's fast.
Yeah, I must have another question. The system image Julia uses by default, that would be nice to be changed on my computer to include all my favorite pictures. Is there such a possibility, like an environment variable which changes the default system image?
It's, as I think I said, that it's a bad idea to change the default system image because, for example, let's say you have VS Code and VS Code will load Julia and then it will use the default system image. And if you have a bunch of extra packages in there, things might look different from what VS Code expects and so on. But what you can do is that, let's say you create a system image with all your custom packages, then you could create a little file that for example, you can create an alias, Julia, which sort of runs Julia, and it has the system image is equal to da-da-da in it. You can put that in your bash RC file or whatever it is that sort of starts with the terminal. So you can basically create your little mini Julia command that starts with your custom system image. So that's how you would do that then. Instead of replacing the default one, you would just replace the default command to use the command you're using, you would use that to load the custom one.
And this works then because Visual Studio Code would be linked to another Julia, like by path and not by shell command. So then this does not interfere.
Yes, exactly. So VS Code doesn't execute the command, the alias command, it executes the actual executable. So they would still have the same normal system image.
That's a great workaround.
So I think you can create something called like a shebang script, and you put it in your bin folder somewhere. And you could just call it Julia and then or my Julia, I don't know. But yeah, that's the way you would do it. There used to be a command that replaced the default one, and people used it, and then people like VS Code maintainers got bug reports and things were not working because people destroyed their own sysimage, and then their Julia didn't work anymore, so they had to reinstall Julia. So I actually removed that functionality, and I think that was a good choice.
Thank you for the insights. One further question. Is it possible to inspect what is there inside the system image?
Well, there are a few different ways to inspect it. It depends on what level you want to see. So let's say we go to the compiled here, and then so here we have a sysimage that is in this compiled app sysimage. So one thing you can do is you can list all the symbol that's in here. This is all the different symbol, as a lot of them. But the easiest way to figure out what's in the sysimage is to just start Julia with that sysimage, and then you have a Julia session here with everything that's in the sysimage, and you can sort of just look around. So there's one thing called, this is a bit internal stuff, but there's one thing you can see what are all the loaded modules in the sysimage, and we can see here we have this CMGUI, JLL, JLFW, JLFW for OpenGL graphics and so on. And let's say if we go, I mean, we have all the stuff in here, just like the packages would be loaded. So that's the best way to sort of interact with the sysimages, to load it in Julia itself. There's not that many tools from outside Julia that can list things that are inside a sysimage. You can call strings. This is a standard Julia command that you can do to, well, not a Julia command. This is a standard program to find strings inside a shared library. So you can see these are all the strings that are in here. There's apparently a path there, and then you can grep through it. Maybe you want to grep for, oh, that's probably. So here we can see that this is probably a doc string or something that's in there. And there's some path and so on.
Thanks.
Oh, I just noticed my email is wrong here. It says Kristoffer, but there should be Kristoffer.
A question, if no one else in chat is asking. When you created the sysimage with the plots, was that kind of on top of the Julia sysimage? So you had all the default stuff included, or do you have to specify what exactly you want in there?
Yeah, that's a very good question. And there's two choices. There is, let's go back. Let's load package compiler, and then let's get the help for create sysimage. So there is a thing, an option here called incremental, and that if that's true, which is the default, builds the new system on top of the existing one. So you basically get all the compiled stuff that's in it with you, and otherwise you sort of do it more from scratch, and then you only get the compilation stuff from what you actually specify. For apps, this defaults to false, because when you're doing an app, it's unlikely that you want all the, like Julia contains a bunch of compiled code for the REPL, for example. But when you're doing an app, you don't want all the compiled code for the REPL because you're unlikely to even store the REPL. So if I go to the compiled app here, we can actually start Julia with this. This should start with the custom sysimage, and I can do a trace compile on this, and you can see that it has to compile the REPL now because that's not included. But if I go back and I do on the system image with the plots, and I do a trace compile on that, had to compile a slightly bit more than the normal one, but not at all as much as the other one. There are some things here that didn't get cached for various reasons, but it still has the stuff from the default system image, unless you specify this incremental false.
Yeah, and if you do the incremental creation, is that a comfort so you don't have to specify all the other packages, or is it actually faster just to add something on top than redoing the whole thing altogether?
This is more about, like, if you have it incremental, that's the default, then you're going to have a fast REPL and so on, and otherwise it will be a slow REPL. So it will be bigger with incremental, but
sorry, I mean the creation of the sys image itself. If that's faster, if I have an existing sys image and just add a package, or if I have to do all the thing that's in there at once.
As it is right now, it's slightly faster with the incremental one because then it uses the existing one as sort of a base. If you're using the incremental false, it has to sort of create a fresh one with nothing in it, and then it adds the stuff to it. So it's a bit slower to create a non-incremental one, but it's going to be smaller in the end. Typically for normal sys images that you want to just put packages in, you almost always have incrementals equal to true, because otherwise the REPL is very slow, the package manager is very slow, and so on. But when you're creating like apps, you're only going to run only that code that you have in the app, so then you don't need all the other compiled code.
Okay. And one more question. You mentioned that packages that are in the sys images, you can't update them straight away.
Yeah.
If you use PKG, is it actually like a pinned package then, or what happens if you try to update it anyway?
If you have a sys image, it's gonna act like it's pinned. So I don't think, actually, let's see, because there was an update to. Did I update my manifest now? I have to check this. So we have plots here now. We don't have PKG version 1.8? No. So, okay, this is what I wanted to show, I think. So here we have this FSF JLL in the sys image, and it's at 0.29, but the most recently released one is at 0.30, and it's being blocked from update because of sys image. So the package manager knows what's in the sys image, and it's not going to update things to versions that are different. Like if I try to do add FCF JLL at 0.30, I try to force it to go 0.30, it should, yeah, it's saying here the possible versions are only at 0.29, and then it says package and sys image with exclamation point. So you're only allowed to use 0.219. You can't use anything else because it's in the sys image. But of course, if you start Julia with, there's like a way around there. If you start Julia without this, now I'm not running this sys image anymore. So now when I update, I'll probably get the newest. Oh, I did not get the newest. There might be some other reason why I'm not getting the newest, but when I force to get the 0.30, okay, it's been something with plots that it's not compatible with the newest one. But anyway, now I could install this that I couldn't before. And now if I start with Julia with the sys image again, it looks like, okay, or was it FCF? It looks like it's at 0.30, but actually in the sys image it was at 0.29, and 0.29 is what actually will be. So you have to be a little bit careful. You can't just take a project and manifest from somewhere else and put it with your sys image, because then it might not be the same that gets loaded that's in PKG status.
Maybe one last question from the chat. Is also distributed.jl possible to be put into this image?
Yes, I think I have fixed that before. It wasn't, but or wait, in a sys image. Distributed.jl is already in a standard library and it's already in the sys image. I thought that the question was going to be if you can put it in an app.
So there was a rephrasing from my side. The original question was like, I can see how sys image can work with multi-threading, but what about multi-processing?
I mean, when you do multi-processing, you're starting multiple Julia processes, and all of them load the sys image. So if you want to load a package on multiple Julia processes, like let's say you want to do some distributed thing with plots, then instead of having to load plots on every new Julia process, like the normal way, you could load it via the sysimage way. And in fact, we can, let's say I do this, and I do, and then I should be able to do like, something like that. You can see that was pretty fast to load plots on a bunch of, on all these workers, but now if I do, oh, now it has to even pre-compile here because it's, okay. So this is going to take forever now, but my point still stands, sort of that using the custom sysimage, I think that works just as well for sort of distributed things when you have multiple processes.
Thank you. I think that it's a good time to kind of, yeah, have a stop. And we kind of still, I have some more time to be there for questions. I'm not sure about you, Kristoffer, but anyway.
Yeah, I think I have to leave pretty much now, but yeah.
The better, it's good, yeah. So then thank you very much, Kristoffer, for being our guest today, our speaker. It was very insightful with a lot of questions also from you participants. Thank you for all the interactivity, for the deep dive questions and yeah, all your input. It was a lovely session.
Yeah, thanks for all the questions. It's always nice when you see some interest from the audience, sort of. So it was fun.